So we've defined probabilities and also seen the couple main ways to find probabilities, namely the classical method and the empirical method. And we've already seen a whole bunch of rules kind of pop up on us. First rule is that every probability must be greater than or equal to 0 or less than or equal to 1. In other words, as low as 0, as high as 1, but no further than that. And the sum of all the probabilities in the sample space must equal 1. Kind of obvious. You have to have 100% of your outcomes accounted for during your entire sample space because the sample space is the list of all possible outcomes. An impossible event, say like a red spade, would have a probability that is equal to 0. And a certain event, so think back to that classical example with the cards, so aces or higher would be 100% or 1. Right? Because something in the sample space has to happen. Since it's the entire sample space must equal 1. If it's certain to happen, then you're basically accounting for your entire sample space. So it's kind of unusual, but it could happen. An unusual event would be less than 5%. We learned that back in section 3.2. It was when we learned the empirical rule, funnily enough, in section 3.2. So less than 5%. Don't forget that piece because that's a big piece and very important for us. Now, a probability model is going to matter to us because we want to kind of take these ideas that we're kind of dancing around, probability of this, probability of that, and we kind of want to systematize it. We want a table or a chart. Sometimes it'll be a graph. I should add that, or a graph form, where we can see all the probabilities and their outcomes. So these are both tables. So I have here two probability models, and you're trying to determine whether these are valid. So you have different outcomes, and these are the probabilities. Well, don't worry about the -2. -2 is fine. Where you care about negatives is in the probabilities, because all probabilities have to be between 0 and 1, and they must add up to 1. So we have to check those numbers. So 0.5 plus 0.1 plus 0.05 plus 0.35. And sure enough, it makes 1. So this one on the left is valid. The one on the right is 0.3 plus 0.4 plus 0.1 plus 0.3, which is not valid. It's not adding up to 1. Right? There, and I just typed all that up for you. So every probability is between 0 and 1, and the sum of the probabilities is 1. So this one's valid. You don't actually need to mention about the other probabilities. Once you have one of the things not working, then you know it's not valid. So the sum of probabilities is 1.1, which is not 1, which is what we want. And since it's not making 1, then that's not a valid probability distribution. So you can see both of these are, well, this one on the right is not, but the one on the left is a probability model. It's listing all the outcomes, right, all the possible outcomes and their associated probabilities. But I don't want you to think that there's only one way to write a probability model. That can get a little dicey. So this next example is just to show you that you can actually write the same probability experiment a couple different ways depending on what you're interested in. So in this particular example, I've got the biological sexes of two children. So I have their biological sex here, MM, MF, FM, FF, so on. And I have the probabilities associated with each. So let me highlight the different columns, or excuse me, the different rows. It's quite a hideous combo of colors there. All right, so I've got MM up here, right? They're in kind of this aqua color right here. So there they are. And then I've got my MF, right, male, female, then female, male, and they're in kind of an orange color. And then I have FF down here in pink. So that's the same as FF right here is if you want to record number of girls, that would be this group, right? So 2 girls. And if I want MM, that would be no girls, so that would be this group. And then the middle group would be the mixture, right, MF or FM, and that would be the orange group. So you can see they're both valid, right? They're just different ways of looking at the same experiment. And that's just one thing I wanted you to note right there. So that's what I wrote for the example here. So both these tables are valid. They're valid probability models. So they list all the outcomes and their probabilities, associated probabilities, for the same experiment. There, I just put that in there. They just organize the data in different ways. So this one on the left, this is actually, sorry, this is actually more of a chapter 5 way of organizing it. We're going to consider the order of the children. So which one's first, which one's second, we organize it differently. This one over here, we're actually going to hit more on in chapter 6. So particularly, well, both 6.1 and 6.2, the two sections we're covering, where it's considering the number of girls. So it's grouping outcomes together for the sake of convenience. Namely, in particular, the two orange ones got grouped together into that one right there. So that's what it means when it says it groups outcomes together. I'm meaning that orange bit right there. All right, so let's work more on this side of the house then. How do we come up with that list of outcomes, right? So it was listed so nicely and neatly over here on this left-hand side, right? We have to list all the outcomes, so we're going to need to be able to find all the outcomes. And that can be tricky. So we're going to take some time now to kind of come up with some ideas for how to find that sample space. And barring how to find it, at least how to find out how big it is, how large it is. All right, so we want to talk about classical probabilities in particular, because if it's from data, then you can find all your outcomes based on your data. But if it's not, if it's based on classical probability, then you're going to have to be able to hypothetically think of that list over here on the left-hand side. Like, where do you get those from? How do you know you've gotten all of them? How do you know there aren't any more, et cetera, et cetera? So we need to be able to come up with that. And a tree diagram is one of the tools that we use for small probability experiments with only a few outcomes to come up with that sample space, at least all the items that are listed in that sample space. When it gets so crazy or so large that we don't want to use tree diagrams anymore, then we'll expand our idea to something called the multiplication of rule of counting. That'll at least tell us how large our sample space is, even if we don't feel like drawing it all out with a diagram. All right, a tree diagram is an organizational technique. Basically, you're just trying to come up with some kind of tool that will help you find your sample space. And it's just a way of organizing that sample space into a clear, organized pattern, so you know you've got all of them. They all have a pattern to them, so you can figure out their probabilities, that good stuff. So we have the simple tree diagram. It's literally as simple as we can make them, which is for a single coin toss. So you've got your present right here at that little circle. The circle is the present, and you're moving into the future, because remember, probability is the probability of the future. It's an unknown event that hasn't happened yet. So you branch from that O, from that dot, out into two possible outcomes. The outcomes are heads and tails, and each of these little arrows is a branch. Notice we ignored the possibility of landing on the edge. We will do that because in classical probability, it often makes a lot of sense to avoid all of that messiness. So we will do so quite frequently. Now, there's a lot of things to note on these diagrams. Time is moving from left to right. So as we move from left to right, we're going into the future. So the present is where the dot is, and then as you move along the branch, you're heading into a hypothetical future. You always start the diagram on the left and move right. You don't start it any other way. The diagram should be vertically aligned, namely the outcomes should be one right over the other. And then when you're all done, you make a vertical list of at the right of the diagram with all the outcomes. All right, so let's do this together for two children. So suppose you're going to have two children in the future. What could be their biological sex? Oh, biological sexes, right? Plural, because you're trying to come up with this probability experiment. So we're going to assume, for the purposes of this problem, only male and female, which will denote M and F. It's really common to try to simplify things down to just simple letters for these problems, because otherwise they can get pretty ugly. We're also going to assume that they're equally likely. So biological sex-wise, it's not only M and F. There are people that are born with they're called intersexual, so you can look those up in online. And then you also have your, or a biology textbook, and then you also have your equally likely bit, which is not actually true. Male and female are not equally likely, but they're close enough for our purposes that we're going to count. All right, so the way this works is we want to start on the left and move to the right. We want one branch for the first child, and then we branch off of there for the next child. And here it is. So I've got right here at the beginning of the green ones over here is the present. And then I hypothetically move to the future. So I could have a male child in the future. And then after having that male child, I could go off and have another child. So from that first male child, I could have another male child. From that first male child, I could have a female child. Back to the present, I might not have had a male child at all. Maybe I had a female child, so I'm working on the bottom arrow. So I move along this bottom arrow to a female child first. And then from that female child, I could have had a male child. Or from that female child, I could have a female child. So it gives me the sample space, MM, MF, FM, and FF. But, they're in a nice pattern. They're equally likely. They're all organized. Everything's beautiful. All right, so let's define the event G. When having two children, both are female. Now define, what they mean is just tell me what outcomes are in this. That's all they mean by that. So having two being female would be FF. That's all it is. Both are female. Simple as that. Is that a simple event? Oh, that's a little kickback to a little while ago. And the answer is yes, it is a simple event because there's only one outcome out of the 4 in the sample space that has this. There, done. Before we go, make sure you understand the point of this. So you're creating a diagram that takes the present, which is over on the far left, and imagines hypothetical futures for this probability experiment. What are the possible outcomes of this future experiment? And you get a nice, clear, organized list, and that would help you come up with the list for your probability distribution table if you wanted to make it. That's what you're trying to do. You're trying to create that sample space with these tree diagrams.